Elementary algebra. Elementary algebra is the type of algebra that one might learn in high school in the first year of college. It is the study of the arithmetic of real numbers and some elementary functions of a single independent variable. This includes how to manipulate algebraic expressions that include unknown quantities, as well as solving equations and inequalities for those unknown quantities. This also includes the introductory study of single variable real-valued functions, such as polynomial, rational, radical, exponential, and logarithmic functions. This may also include a basic introduction to linear systems of equations. Abstract algebra. Abstract algebra is the study of algebraic structure. It includes studying algebraic systems where abstract operations are applied to a set of elements. These operations are assumed to follow a set of rules called axioms. Such systems are then studied abstractly, meaning that the operations and elements are not concretely defined, but left general so that the results might be applied to any concrete system where the behavior is observed. A variety of algebraic systems are well understood. These include, but are not limited to, the following. Groups. These are sets that have one operation defined on them that satisfies the group axioms. If the operation is commutative, then the group is called Abelian after Niels Henrik Abel. Some examples of groups are the integers with addition, the non-zero real numbers with multiplication, permutations of a set with the operation of doing the permutations in succession, and the moves on a Rubik's Cube with the operation of doing the moves in succession. Rings. These are sets that have two operations defined on them that satisfy the ring axioms, one referred to as addition, the other as multiplication, though they do not have to be the operations with those names defined on the real numbers. If the multiplication operation is commutative, has an identity, and every non-zero element has an inverse, then the ring is called a field. The integers with addition and multiplication are a ring. The rational, real, and complex numbers with addition and multiplication each are fields. Square matrices with addition and matrix multiplication are a ring. The integers modulo n for some positive integer n are important rings that play a role in cryptography. Vector spaces. These are sets of objects referred to as vectors that form a group under an addition operation, but are also associated with a field of scalars and have a scalar multiplication defined that indicates how to multiply a scalar and a vector to obtain another vector. Geometric arrows in n-dimensional Euclidean space, column or rows of numbers, matrices, and polynomials of degree at most n are all important examples of vector spaces. Many data structures are another important example of vector spaces. Modules. These are similar to vector spaces, but instead of having the scalars come from a field, it is only required that the scalars form a ring. If the ring is not commutative, then the module is defined as either a left or a right module depending on which side the scalars will be on. K-algebra. These are vector spaces with a field of scalars called K, where a bilinear product is also defined on the vectors. Hey, what's purple and commutes? An abelian grape. And if you like that joke, hit that subscribe button. And if you didn't, hit the subscribe button anyway, because we want you to be part of the Scholar Sauce community. All right, let's get back to the video. Group theory. Group theory is the branch of abstract algebra that studies the properties of the group algebraic structure. This includes understanding functions or maps from one group to another that preserves the group structure of both spaces. Such a map is called a group homomorphism. If the homomorphism is also one-to-one and onto, then it is called a group isomorphism and shows that the two groups have indistinguishable structure. Group theory includes studying groups in the abstract as well as applying those ideas to groups observed in the real world. Some important group theory ideas and results include normal subgroups, quotient groups, the classification of finite abelian groups, the Suloff theorems, Lagrange's theorem, and the three-group isomorphism theorems. Group theory has applications to quantum mechanics, crystallography, analyzing molecular vibrations in molecules, cryptography, error-correcting code, DNA structure and protein folding, and more. Ring theory. Ring theory is the branch of abstract algebra that studies the properties of the ring algebraic structure. Similar to groups, there are structure-preserving maps from one ring to another called ring homomorphisms. If they are one-to-one and onto, they are called ring isomorphisms and show that the two rings have indistinguishable structure. Ring theory includes studying rings in the abstract as well as applying those ideas to rings observed in the real world. Some important ring theory ideas and results include ideals, quotient rings, polynomial rings, principal ideal domains, the three ring isomorphism theorems, the division algorithm, and the Chinese remainder theorem. Ring theory has applications to solving Diophantine equations, cryptography, and algebraic geometry. Arguably, real and complex analysis are an extension of the study of the fields of real and complex numbers, respectively, and the study of functions on those sets. Field theory. Field theory is a sub-branch of ring theory that studies the properties of fields in abstract algebra. Because a field is a ring where the multiplication operation is commutative, has an identity element, and every non-zero element has an inverse, it is essentially a set where an addition, subtraction, multiplication, and division are all defined. This includes the well-known sets of the rational numbers, the real numbers, and complex numbers. However, it also includes the fields of rational functions, algebraic number fields, and finite fields such as the integers mod a prime number. Many fields can be realized as field extensions of another field. For example, the complex numbers are the real numbers extended by the number I. An important type of field extension of a field is called a splitting field of a polynomial with coefficients in the original field. This is the smallest field where the polynomial factors into linear factors. Such splitting fields are related to a corresponding Galois group, which we will reference again in a moment. Fields have many applications in mathematics and other fields of study. These include geometry, linear algebra, algebraic geometry, number theory, cryptography, error-correcting codes, and data transmission. Also, essentially all the sciences, including physics, chemistry, biology, earth science, computer science, etc., use either the real or complex number systems, and hence are applications of field structures. Galois theory. Named for and introduced by Évariste Galois, Galois theory builds a connection between group theory and field theory. The fundamental theorem of Galois theory relates certain field extensions to what's called its Galois group and builds a correspondence between the field extension's intermediate fields and subgroups of its Galois group. The topic of Galois theory was introduced to understand how to solve for the roots of polynomials. Galois was able to build a connection between polynomials that are solvable by radicals and whether its corresponding Galois group was a solvable group. This allowed for characterizations of many ancient problems, such as whether a compass and straightedge can be used to trisect an angle, or used to double a cube, or whether a general degree 5 polynomial can be solved by radicals. Galois theory produces proofs that each of these things are not possible. In fact, a general formula for solving a degree 5 or higher polynomial is not possible because many of the Galois groups corresponding to those polynomials are not solvable groups. While Galois theory itself may have limited applications to real-life problems, the development of Galois theory was an important motivator of group theory in general, and as such is connected ancestrally to all the myriad applications of group theory in the modern day. Linear algebra. Linear algebra is the study of the algebraic structure of vector spaces. Vector spaces are one of the most ubiquitous algebraic structures. Loosely speaking, a vector space is a space of objects that can have an n-dimensional grid placed on it and uses a collection of master directions called basis vectors to identify where vectors are located in the space. These spaces often have an inner product defined on them, which provides means to define lengths and angles and hence a geometry of the space. Linear algebra also discusses structure-preserving maps from one vector space to another. Such maps are called linear transformations. If they are also one-to-one and onto, they are called linear isomorphisms and show that the vector spaces have identical structure. Many important operations and functions are linear transformations, including reflections, rotations, scalings, shears, projections, the integral, the derivative, and other differential operators. Linear transformations between finite dimensional vector spaces can also always be represented by a matrix, and there are many results about matrices and transformations that are incredibly useful and important, such as determinants, eigenvalue-eigenvector problems, diagonalization, symmetric and Hermitian matrices, orthogonal and unitary matrices, canonical forms, and various matrix decompositions. Linear algebra has important applications to calculus, real analysis, differential geometry, ranking algorithms and search engines, linear programming, signal analysis, computer graphics, data science, machine learning, quantum computing, quantum mechanics, electromagnetism, electrical circuits, stress analysis, least squares approximation, genetics, graph theory, cryptography, Markov chains, economics, finance, Riemannian geometry, general relativity, and many more. Numerical linear algebra. Numerical linear algebra is the intersection of numerical analysis and linear algebra. It includes the development, analysis, and application of practical and efficient algorithms for solving linear algebra problems. Two main focuses of such algorithms are efficiently solving systems of linear equations and efficiently computing eigenvalues and eigenvectors of linear transformations. Numerical linear algebra has the same applications as linear algebra, but is focused on numerical computations. These include applications to physics, mechanics, chemistry, finance, and more. Geometric group theory. Geometric group theory is the intersection of group theory, geometry, and topology. It studies the properties of groups by investigating the geometry and topology of the spaces that they act on and vice versa. It also includes the study of such groups themselves as geometric objects. This is done by applying a metric or length measure on the group. Representation theory. Representation theory is the study of abstract algebraic structures by representing their elements as linear transformations of vector spaces. This provides a simple perspective to study the properties of such algebraic structures and, in many cases, makes it easier to prove facts about those structures. Representation theory is applied in important mathematical ways to understand group actions, Lie theory, number theory, combinatorics, dynamical systems, knot theory, and the Fourier transform. There are applications of representation theory in mathematical physics, mechanics, string theory, engineering, control theory, robotics, coding theory, spectroscopy, crystallography, modeling DNA, signal processing, and more. Lie theory. Lie theory, named for Sophus Lie, is the study and application of objects called Lie groups and Lie algebras. These two classes of objects are related by a function called the exponential map, which creates a correspondence between Lie groups and Lie algebras. Lie groups are a geometric group that is also a differentiable manifold. As such, Lie theory is a branch of differential geometry. Lie algebras are examples of K-algebras where the field K is the real or complex numbers and the bilinear multiplication is the Lie bracket. The structure of the Lie algebra implies the structure of its corresponding Lie group. Aside from applications in solving differential equations, Lie theory has many applications in mathematical physics, where the Galilean, Lorentz, and Poincare groups are all examples of Lie groups. As such, Lie theory is particularly important in general relativity and astrophysics. Category theory. If abstract algebra takes concrete examples that share similar properties and abstractifies them into an algebraic structure, category theory considers the similarity in abstract mathematical structures and abstractifies that idea one layer further to study just that similarity in structure. This provides immense power to find facts that are true about all types of mathematical structures simultaneously. For example, why groups, rings, and vector spaces all have the same three isomorphism theorems is explained using category theory. Thus, category theory has applications in practically every branch of mathematics. However, category theory is also important in many areas of computer science research, such as functional programming and semantics. And that's it for part 2 of every type of math. Today we covered every type of algebra. In part 1, we covered every type of calculus and analysis. You can find that video here if you missed it. In part 3, we cover every type of geometry, which you can find here. If you haven't yet subscribed, please do so now so you can be part of the Scholar Sauce community. And check out our other great content like this video here where you'll find out that classic JRPG world maps weren't spheres. We'll see you next time on Scholar Sauce.